supposed to be a lecture, so I will try to make it a bit more, practical than a usual talk. The idea is to give you some insight so if you look at all the business of fractional phases, of course, we have theoretical models, but we rely a lot on numerical simulations. So the goal of these lectures and the hands-on that we will have tomorrow is basically to provide you the basic idea of how we perform numerical simulations for the systems. This is the outline of the talk. There will be, of course, some overlap with the other lectures. Unfortunately, I have to go once again through the story of the quantum Hall effects in general, and especially the fractional one, because we need, it's the basic blocks of the understanding of the fractional chain insulators. Then I will do some history, how people ended up proposing fractional chain insulators as a lattice realization for the quantum Hall or fractional quantum Hall effect. And depending on the time I have today, I will also briefly discuss the story of fractional chain insulators in Twisted Demo TE2. Part 2 will be a bit more about the latest development in the field, searching for something which is a generalization of fractional chain insulators, namely fractional topological insulators where you don't break the time reversal symmetry, and all the puzzle that we have when we look at a system like the pentalayer orbital graphene. And the tutorial will be tomorrow afternoon with Professor Yu, who is somewhere in the room. And if you already want to know what we will talk about, you can scan the QR code here and have the full tutorial, not the solution, just the questions. Okay, so a brief history of the quantum Hall effects. It's really the first topological phase of matter that was observed experimentally, especially if you look back at the integer quantum Hall effect. I think you all know that topological phase of matter cannot be described by broken symmetry. There is no local order parameters, and you would say that you have a topological phase if there is at least one physical quantity, so something that you can actually measure in a lab that is related to a topological invariant. And the best, the most famous example, and there will be no picture of a donut or whatever, but it's just the genus of the surface. It's a system with a gapped block and gapped or gapless mode, depending on the kind of topological phase that you're considering. This is a typical Hall bar that we use for the transport measurements. We measure the longitudinal resistance, Rxx, the Hall resistance or the transverse resistance, Rxy. And we have this two-dimensional electron gas that we put under a low temperature and a strong magnetic field. And what we develop is Landau levels. I'm sure that all of you have done the calculation of Landau levels. If not, there will be a tutorial about that. And if you measure the longitudinal resistance or the longitudinal transverse resistance, you will see plateau in Rxy, which are well quantized, and a zero of the longitudinal resistance for specific values of either the magnetic field, or if you think about Landau levels, when you have an integer filling of these Landau levels. So the filling factor is defined by the as a function of magnetic field and the electron density n, but you can, in a finite size system, so that's something that we will do a lot when we do numerical simulation, it will just be the ratio of the number of particles, n, over the number of flux quanta that you have in your system. And if you have a finite system with periodic boundary conditions, the number of fluxes tells you how many states you have per Landau level. So it's really the filling factor in the most simplest definition. Once again, it's integer filling. You have the quantization of the Hall conductance or the Hall resistance, which is a universal quantity that is defined with very, very high accuracy. That's why it's used to define the unit of resistance. And as Dee already mentioned this morning, it's a topological phase because we know we can derive that the Hall as conductivity is related to the first Chern number of the band, which is here just a single Landau level. That explains why this quantity is so robust. When you have a system with a bulk that is gapped, it's pretty easy if you have an insulator to picture why the system is gapped, right? You just have to, if you want to create an excitation, you have to overcome the band gap. But let's say if you don't have an integer filling factor, but for example, you go lower than 1. So you take these Landau levels here and you deplete the lowest Landau level. You might wonder why we should have a gap system in the first place. If you just think about non-interacting particles, here are 4 different configurations where you have 2 particles in 6 flux quanta. And all these configurations, they have exactly the same kinetic energy, namely 2 times 1/2 of h bar omega c. So it should be a macroscopically degenerate system. But of course, in such a picture, what we completely put under the carpet is the interaction. And it's not an perturbation anymore because there is no kinetic energy. And the gap phase will only appear for some specific values of the filling factor that is a ratio between 2 integer numbers, so a rational number. The fractional quantum Hall phases, I've already mentioned this morning, is topological phase. In a sense, it has fractional excitations that carry a fractional charge that are free to move in the system in principle when they are not trapped by boundary of defect. You can also, if you think about the SSH model, you do have fractionalization of the excitations, but they are bounded to the edge of your chain. It's not the case for topological order phase. And these excitations, these fractional excitations, they also have not only fractional charges, but they have also fractional statistics. And even after so many years, it's still experimentally a challenge to prove that you do have fractional statistics in this system. So as a brief reminder, what we mean by these anions or these fractional excitations, fractional statistics in, let's say, remember that if you have a wave function with 2 particles, 2 objects, which are indistinguishable, usually what you say, well, if you permit the 2, they should be equal up to a phase. You do that twice, and you should get back the same wave function. So the phase should be 0 for bosons and pi for fermions. But that's a discrete way to think about the exchange of 2 excitations. And if you think about it as actually braiding these 2 objects in time, then in 2 dimensions, you can have something which is a bit more generic than this. And that's what leads you to abelian anions. So something with a phase that will be not just 0 pi, but a fraction of pi. And you don't have to actually get the same wave function. It can be a combination of different wave functions. So in that case, the exchange will be described by matrices, not just by phase factors. And that's what will give you the non-abelian anions. The experimental evidence, there are some recent progress, like a few years ago by 2 groups, including one in Paris, basically trying to really show experimentally the evidence of these fractional statistics. So this picture is the anion collider. And the reason why people were excited a lot by these, especially the non-abelian excitations, is because that's a way to do error code correction in a quantum computer, in a hardware way, not just, not in a software way, let's say. Directly have a system which is protected to local perturbation. That's the example of the toric code. I'm sure that you have seen like a couple of papers recently on using a quantum computer, realizing actually a small version of the toric code. So the idea is not to use actual physical spin, qubits to make a toric code, but directly have a toric code from the system. That's basically what the topological order can give you. So how do we understand the fractional quantum Hall effect? Remember, that's the Landau level, and in the simple picture, when we look at filling factor lower than 1, and for the time we completely forget about the spin degree of freedom, the Hamiltonian of the system is actually very simple. It's just the interaction. Here I take the Coulomb interaction that you project onto the lowest Landau level, let's say, as an example. But you know that because you have this non-commutative geometry, the projection is really something highly non-trivial here. So if you look at, for example, what you get when you have more usual traditional strongly interacting model like the Hubbard model, it's a lattice model, and you have a competition between the kinetic energy and potential energy. For the fractional thermal effect, here you have a non-commutative geometry. You have no kinetic energy. Everything is basically the interaction. And it's long range most of the time. We will discuss about that. And to some extent, it looks more like the quantum chemistry Hamiltonian. So how do we deal with that? How do we how we can investigate such a system from a theory point of view? Actually, it goes back to the very beginning, just after the discovery of the fractional quantum Hall effect experimentally, was to propose a wave function, a many-body wave function, that should be a very good description of the first fraction that had been observed experimentally, namely the fraction 1/3. What basically Laughlin did was to say, well, if you have an electron at link factor 1/3, a very good approximation of what's going on is this wave function. And it's true that just by looking at this, by having this expression of the wave function that looks like, if you look at the density profile of such a wave function, it looks like a droplet of liquid. Even just by the expression here, you can actually, with some tricks, you can extract the nature of the excitation, check that they have a fractional charge. A simple trick is to add one more fluxes in your system, and you will nucleate one quasi-Hall excitation. And you can compute its charge and see that it's a fraction of the electron charge. You can look at the statistics and see it's a fractional statistics and so on. Of course, that's not the only tool that we use. People use a lot of numerical simulations to investigate the fractional quantum Hall effect. You can use also quantum field theory. I think Dee will talk about tomorrow about the Shankar and Murthy approach, which has some flavor of this. So there are many ways you can try to prove this system. But as usual in physics, what we like is when we have a model that we can solve analytically to understand what's going on. So if you're interested, and there is actually an extra tutorial that you can download here and have fun to derive the Haldane potential. Let me give you quickly the solution of this tutorial here. Simple problem. We assume that all the electrons are spin polarized, so the spin doesn't play any role here. And we only focus on the lowest Landau level. So you did the exercise of the Landau levels in the symmetry gauge, and you know that the wave function, the one-body wave function, have a very nice expression. It's basically proportional to some normalization factor to z, which is the electron coordinate in the complex plane, x plus iy, to a power m that corresponds to the angular momentum of your electron, times some Gaussian weight. Oops, the LB should be here, sorry, it's z modulus of z squared over 4 LB squared. If you work in the lowest Landau level for an arbitrary number of electrons, let's say n, any many-body states can be written down as a polynomial in the complex coordinates of your n electrons times a global Gaussian weight. So that's why most of the time, if you look at the literature about fractional quantum Hall effect and model wave function, people actually omit this term here because they only look at the polynomial part, which is the non-trivial one. As I said, we want to be able to solve at least one case. And to do that, we only consider two particles. So let's take two particles, but we don't specify the interaction for the time being. It's just an interaction, repulsive, let's say, but it doesn't have to be actually, that only depends on the distance between the two particles. And we project that onto the lowest Landau level. So it's basically the Hamiltonian I was writing down here, just with the generic interaction. So if you want to basically get the spectrum of this Hamiltonian, you have to diagonalize it. You could say, well, it's a two-body problem, so I need to find the basis first. The simplest basis I can build is just the tensor product, particle 1 and particle 2. So that's the tensor product basis. So it's Z1 to the power M1, Z2 to the power M2. But it's not the most convenient one. Actually, as usual, it's way better to work in the center of mass and relative coordinates. So you can actually use this basis, which is equivalent to this one, where you have the center of mass to the power capital M and the relative motion between the two particles with a relative angular momentum M. So that's okay, that's a basis. A first remark, M encodes the statistics of your underlying particles. If you have two electrons, they are fermions. So the wave function here should be odd when you exchange the two particles. And it's only possible if the value of M is odd. And actually, this basis is directly diagonalized the Hamiltonian that you have here, because V only depends on the distance between the two particles. So you don't care about the center of mass motion. And it's pretty easy to show that these states are actually eigenstates with an eigenvalue V of M. So using this basis, we have diagonalized the two particle problem exactly in the lowest Landau level. The VM, they have a name. They've been introduced by Haldane back in the 84, if I remember correctly. And they fully characterize your interaction projected onto a given Landau level. Here I did the exercise for the lowest Landau level, but you can do that for any Landau level. In the tutorial, you have actually, we guide you to get the derivation for the Coulomb interaction. It basically, the potential scales like 1 over M. This is a picture. Fortunately, the dots are a bit small. So in red, that's the V of M for the Coulomb interaction projected onto the lowest Landau level. And in blue, it's in the second Landau level. As you can see, it's slightly different because, for example, the V2 is larger than the V1 in the second Landau level. So the structure of potentials will, even though you use the same interaction, if you use them in a different Landau level, they would have a different structure. So that's nice, but it's not possible to solve the case for the Coulomb interaction for more than two particles. But it's doable for at least one interaction, which is the hollow core interaction. So the idea is the following. You take all these potentials here, and you kill all of them except the V1. So that's basically what this definition here means. So that's why the hollow core interaction, you will find it's also under the name of the V1 interaction, just because you take all the potential to 0 except V1. And, well, you know the spectrum, so you know the eigenstates for the two particle problem. And especially if you look at this state where you take the center of mass, we don't care. So let's put the capital M to 0, but let's look at M equal to 3. That's the smallest value for the relative angular momentum, where the actual, if you apply H on this state, this will give you 0. If you take a larger M, this will also be 0, but that's the smallest one where you will have a 0 energy state. And if you look at the expression here and compare to the expression that was here, it's just the same here for two particles. And basically, it tells you immediately what is the function, what is the role of the Laughlin state. The Laughlin state has as a feature that it's the unique densest zero energy state that completely screen the V1 interaction. The V1 interaction is seen like as the shortest component of the interaction. You might wonder in which case this is a good approximation. I mean, statement is true only for the model interaction. And this is where we start relying on numerics to check the assumption of the Laughlin state being a good approximation. That's an example. You can do that for the Coulomb interaction. So usually the simplest thing that you can do is you get the ground state at 1/3 for the Coulomb interaction, and you compute the overlap with the Laughlin state, just a scalar product between two vectors, and it gives you a number between 0 and 1. And it's usually pretty high for the Coulomb interaction. of the order of 0.96, 98. So very close to 1, even though the Hilbert space by itself is exponentially large with the number of particles. But now if you ask me, okay, if I take another interaction, if you don't take the Coulomb interaction, but some slightly different, like a screen one, or an interaction that can cook up by just providing the potentials, will it be like at 1/3, will I get the Lofton state as a good approximation of the ground state? Well, it's not a simple answer, actually. There is no generic rule for that to say, if you have these potentials, then you should get the Lofton state at 1/3. Here is an example where we only consider V1 that we set to 1 as the energy scale, and we tune V3 and V5. Remember that for fermions, you only care about the odd potentials due to the fact that the wave functions are meaningful for fermions when n is odd. This is the gap in this phase V3, V5 phase diagram for different system sizes, different number of particles. And this is the overlap. And you see when you set, of course, all the potentials, V3 and V5 to 0, but keep V1 equal to 1, where you know that the Lofton state is the exact ground state, the overlap is really close to 1. And at some point, if you crank up V3, it's not that sensitive to V5, but to V3 quite a lot. So there will be a phase transition to actually a state that is gapless if you have a V3 which is too large. But as a thumb rule, in which case is the physics of the fractional the Lofton state relevant for at 1/3? If you look at the interaction, you would say, well, if I compute the potentials, and I see that the V1 is by far the most dominant potential, there's a high chance that you're at 1/3, you're in the Lofton phase. No, in the sense I can cook up interaction which is still long range but will not be in the Lofton regime. And I can cook up something like, so once again, the more you go into, the more VM you are, the more long range you are. Of course, it depends a bit on how it's scaled, a function of M. But you see here, this model is very short range. V1 and V3 are the two short range components, and still it's enough to kill your state. So it's not only about the long range behavior of the wave function. It's basically what's going on once you project into the lowest length over that matters. So since I've shown you some numerical calculations, how do we deal with that for the case of fractional quantum Moiré effect? Once again, you cannot rely easily on perturbation theory, especially if you think perturbation theory seeing the interaction as a perturbation of the kinetic energy, because there is no kinetic energy here. Everybody has the same kinetic energy. You're dealing with a many-body quantum problem. So it means that the size of the Hilbert space that you have to deal with grows exponentially with the number of degrees of freedom that you consider. Think about a bunch of spin 1/2. If you have n spin 1/2, the Hilbert space goes like 2 to the power n. The same story here. Quantum Monte Carlo, it's a system with frustration, so it has some caveats when you try to look at FQH using Quantum Monte Carlo. For fun, this is the amount of memory that you need. Let's say you have the Lofton state and you want to decompose it onto a Slater determinant basis, which is usually what you do when you do numerics. Well, you see how many 10 to the 10 megabytes for around 22 particles. So that's just an insane amount of data that you would have to store. If you want to see the exponential of the Hilbert space, here it is. We have discussed about educated guess. That's basically what the Lofton state is. It's give you a variational state without any variational parameters, actually. You can use composite fermions, which captures very well many of the fractions that we observe here. People use a lot exact diagonalization because first, it's not technically too difficult, at least at the beginning. It has the only big limitation is about the system size. So you have to deal with the finite size effect. The size of the Hilbert space, basically, it's like on the order of 1 billion. You can use a lot tensor network. A matrix product state or GMRG. That's also a very convenient tool to study these systems. There is one good thing about studying FQH in numerics. The actual correlation length is short. So namely, you don't need 10,000 particles to reach something which is close to the thermodynamic limit. But still, you have to be slightly careful. So once again, the goal of these lectures is to try to give you some insight of how all these papers doing numerical simulations about FCI, what is under the hood, right? And one thing is about everybody, whatever the techniques, you have finite size effect. And FCIs can be seen like as, some kind of, or more precisely, the Landau level physics is like the best work case. Everything is very nice. The Landau level has a very flat, zero delta flat and so on. So it's the perfect world. But even there, you have to deal with finite size effect. 1/3, V1 interaction, so the model interaction for the Laufman state. The funny stuff is the Laufman state, we know it's the exact ground state of the V1 interaction. But if you ask me about excitations, especially neutral excitations, we don't have any analytical expression for the neutral excitation on top of the Laufman state. We do have good approximation, but there is no like mathematical expression for these. So we rely on numerical simulations to try to extract the gap. That's the gap as a function of 1/n for the model interaction. And as you see, so we put that on the torus, which is like the Brownian zone. We can use different shapes. And of course, well, depending on the size, you still are affected by which geometry you take for your Brownian zone or for your torus. And you still see some fluctuations of the gap, but they are pretty tiny. And the reason why is, if you look at the correlation length of the Laufman state, it's something which is on the order of 1.4 metric length. This point here was done for 14 particles, which give you a Hilbert space of around 100 million. The size of the torus, one of the great circle, is typically on the order of 16 metric length. So it's like 10 times the correlation length. So of course, everything will decay exponentially pretty fast, and you're in the safe region here. Now, if you take the Coulomb interaction, once again, only Landau levels. Well, of course, here, I don't show the gap up to 0. So these are, fluctuations of a few several %. But nobody will believe that the gap will collapse when you increase the system size to 0. But you see, they still have like major finite size effect, even for the Coulomb interaction in the lowest Landau level. So that's one of the difficulties if you want to do any simulations for FCIs. You will be in a system which is worse than this setup. So they hope to do an extraction of the gap in the thermodynamic limit for the FCI is actually pretty thin. Yep. Yeah. So it's a very good question. Remember, the Hamiltonian is just let's take this one. It's just the interaction. So the scale is always a difficult question, because if I multiply my interaction by 10, I multiply all the energies by 10, right? So of course, for the Coulomb interaction, it's pretty natural. You define it as like in units of E square over epsilon LB. That's natural units, and that's basically the units that are used here in this figure. For the V1 interaction, well, it depends slightly. So there is a very nice way to define it in a manner which is independent of the global scale that you will put in front. If you look at the 2-particle spectrum, there will always be a maximal energy, right? So you can always set this to be basically your scale of the interaction. And then all interaction will be, or all gaps will be defined with respect to this energy scale. And actually it works pretty well to compare different systems. So if you do that for fractional channel insulators, so you basically do your many body simulation with n particles, and you normalize the gap that you obtain by the typical energy scale that for the two particle problem, you will see that whatever the FCI you look at, you get roughly the same gap. If you don't, of course, change the interaction. But that's for the numerics. Once again, it's not only about numerics. After all, we are doing physics, it's really the experiments. And even if in terms of numerical simulations or understanding of the FQH, people have made massive progress over the years. I think it's nothing compared to the progress that we have seen in experiments like improving the samples, improving the mobility, and like having like a wealth of fractions that is observed in the experiments. And that's really like the 40 years of history of the FQH. Okay, how much time do I have? Half an hour, okay. Should be fine. Fractional effect, so okay, now let's move to the FCI. Already addressed this morning, can we get a Landau level with a magnetic field? The answer is yes. This was proposed by Haldane in '88, and basically it's like a churn band that you can obtain in a simple tie binding model. So can arise just by the band structure itself. And so a channel insulator is an insulator with a band having a non-zero channel number. That's the definition. And a very nice way maybe to think about the channel number is to say, well, it's basically the number of fully, if let's say I have n5 states and I want to localize as many as possible, like exponentially localize. If you try to and still have an orthogonal basis, what you will see is that you're able to localize n5 minus c of them, and one will be fully localized. So that's another way to get an intuition about the churn number. And it also tells you immediately, I mean, the reason why you have this, like a Landau level, why you have always this interplay between, more precisely, why a flat band, which is what a Landau level is, can still have something non-trivial, because basically you cannot exponentially localize all your states. Otherwise, it would be a trivial problem. Right? There's definitely some frustration between the churn number that imposed that some states are delocalized and the interaction. A very good exercise, I think, that we will do tomorrow, maybe not on this model here, is to actually see the churn number by taking any lattice model. Here it's 2 orbitals per unit cell with some well-defined hopping terms. You look at the band structure of if you put periodic boundary conditions in both directions, and well, you have 2 separate bands. You can, of course, compute the churn number of each band. That's something that we will do tomorrow. But you can take the same system and open the boundary condition, let's say, in the y direction. And now you will do is basically to project everything on the kx axis. And depending on the parameters that you have picked for your system, you will see edge modes appearing in the spectrum, and then you can actually check in your calculation that these states are localized at each edge of your system. So it's a very nice way to see the edge mode. You can actually see that in your code. So experimentally, how do we reach the zero field and higher temperature, which is another crucial ingredient that I put under the carpet here. All of this, is, of course, was done at, all the data I've shown at very little temperature, like from 10 to like maybe a few hundred Kelvin, millikelvin. Basically, in 2013, you have groups that have shown that you can get the chain insulator or the quantum Hall effect with a well quantized Hall conductance in the absence of an external field. It has concrete application because in metrology, as you use the Hall effect as a way to define the unit of resistance, that's one way where you don't have to deal with the magnetic field in principle. So you can have in your lab something that will define the quantum resistance standard without any external field. And potentially, if you're able to crank up the temperature, you don't need to go to cryogenic temperature, at least not sub 4K. But the question then was, okay, that's for the integer case. What about the fractional case? If you think about the ingredients that we discussed about the Landau levels, what do we need exactly? Flat band. We'll discuss exactly what we mean by that. Some interaction. We basically, at least we would like to avoid band mixing, at least for the, to start with. And of course, a non-trivial chain number. Actually, that's what is an FCI. But as usual, people have been thinking about the role of a lattice well before the proposal of FCIs. It goes back to Kalmeyer and Laughlin. They tried to do a realization of the Laughlin state in a spin system. Colin Reed has a very nice paper from the early 90s discussing about the interplay between the lattice and the fractional quantum Hall effect. And in 2000s, in a slightly different field in cold atoms, they were interested to also engineer fractional quantum Hall states. All I've discussed about fractional quantum Hall state, and actually if you look at the two-particle problem, you see that it does not depend on the statistics of your underlying ingredients. So you can do that with fermions, that's what we do in condensed matter, but you could also do that in cold atoms with bosons. So the idea was, can we reach the analog of the quantum Hall regime or fractional Hall regime in cold atoms? There is one big difference. In cold atoms, your atoms are neutral. So you cannot apply a B field and make them rotate like to create Landau levels. So the idea was to use a lattice for that. And basically do the Hofstadter model and plug strong interaction in. So have a look at the paper of Afezi and Demler, and also Nigel Cooper and Gunnar Moller about that. That's a very nice paper that contains lots of information about something which is very the same line than the fractional chain insulators. Then, like a few years later, several people have proposed system based on electrons and simple lattice models to get these FCIs. So tomorrow, the tutorial will be about this example that I will try to briefly overview today. The Kagome lattice, so we take electrons, no spin. Actually, something that's, for example, you can realize in cold atoms if you really want to. We make it very simple. We have only the nearest neighbor interaction, but with some phase factor. Depending on the phase that you plug in, you will have a system with 3 bands with 3 different chain numbers. And that's the tie binding model that you will derive tomorrow. That's actually the band structure, the energy of Kx and Ky, and here you have 3 bands well separated from each other with chain number 1, 0, and -1. So if you want to mimic what's going on for the FQH, you want to be, let's say, I want to focus on this band and do a partial filling of it. What I would like to have is something where the typical interaction energy scale, EC, is bigger than the spread of the band. Maybe I can show it here, but somehow smaller than the actual band gap. If I'm in such a regime, that's something which is very close to one isolated Landau level. That's a simplification. You can really take the model with all its full glory and band mixing. That's an interesting story. But let's say we are in such a setup here, that basically we can take the Hamiltonian with whatever number of bands and just project onto, so we can first make it flat and then project onto the lowest band. And if it has a non-zero chain number, it's basically like an endo level. Let's try to see if we can stabilize the Laughlin state at 1/3. Basically, knowing that the Laughlin state is the exact ground state of the V1 interaction, we want to have an interaction in the lattice that mimics what is the V1. So the shortest range interaction that you can have between electrons, and on a lattice, it's just the nearest neighbor interaction. This is basically what will mimic the V1 pseudopotential Hamiltonian. That's another example. If you want to do for a boson, you just take the Hubbard term, and that works perfectly. You can do other lattice if you want. There are plenty of papers doing that. So now if you say, okay, I have my setup. I know exactly what I want to get in terms of system I want to simulate. What would be the signature that I look for in my numerical simulation? You can do exact organizational geometry, but you can look roughly at the same kind of signature. You can look at the flow of the twist of the boundary conditions. It's basically like the Laughlin argument. The Laughlin argument is one way to explain how you have the quantization of the whole resistance. And you can see it as we inserting a flux in your system. And you can also mimic that for an FCI by twisting the boundary conditions. There are lots of things about entanglement entropy, entanglement spectrum, particle entanglement spectrum, which is one way to probe your quantum many-body states. I will not talk about that today, but there are plenty of papers dealing with it. Sometimes you're able to compute overlaps with model states. I think Dee will talk about it tomorrow, maybe, if he has time. You can also look simply as the density as a function of k. Is it uniform if it's like a droplet, like you have for the Laughlin state, it should be uniform in k space. If you look at the density as a function of k for your ground state. So that's another signature we can look at. Spin polarization. I didn't talk about spin for the moment, but if you think about twisted MOT2, it's a system where you have two values which are locked with the spin. So if you want to have, let's say, an FCI, usually the first thing that you need to know is to polarize your system in one value. That's the signature. One simple signal that you can get, that you can look at, is the degeneracy of the ground state. So something I didn't talk about until now, topologically all the phases, they have this very nice property that was mentioned this morning, that depending on which geometry you put your system, the ground state will have a different degeneracy. So what I mean here is, for example, if you put it on a sphere, you will have one state separated by a gap from the rest of the spectrum. But if you take the same system, but put it on a torus, now you will have, for example, a threefold degeneracy. Technically, it doesn't have to be exactly degenerate for a finite size system. It should be exponentially the splitting bit should be exponentially small with the system size, and also with a gap. And actually, you can show a relation between having fractional statistics, fractional charges, and topological degeneracy. Basically, if you have two of these ingredients, you have the third one for free. But having, for example, a threefold degeneracy in your numerical simulation is not enough to show that you have a topological ground state. A charge density wave, commensurate one, can have also a threefold degeneracy. That's an example of, if you do a numerical simulation of a typical energy spectrum for an FCI, where you plot the energy as a function of momentum. So of course, rather than plotting 3D plots, what we do is we linearize the 2D momentum. So for example, here, if we have a system that should be maybe a 4x6, so we have 6 unit cells in one direction, and maybe the y direction and 4 unit cells in the x direction, what we do is we define a linearized momentum, which is kx plus 4ky. Of course, for each kx and ky, there is a unique number and vice versa. It's a more convenient way to represent the outcome. And you see that, without talking too much about the detail where the spectrum come from, but we have this kind of, threefold degeneracy, not strictly exact. It's exact if you look at the Laufman state, for the fractional conformal effect, or for any interaction actually, because there is actually symmetry protecting that. In the FQH language, in the FQH case, not for the FCI, and a gap. There is also, where these states appear in the Brillouin zone, is an information that is related to the nature of the states. It's not unique, depending on the case, the geometry that you have. So once again, it cannot be the only signature, but it's definitely one that you satisfy to get an FCI. Yep. This one, integral spectrum, usually is pretty robust. There is you can make the difference between Chauncey wave and an FCI. Overlap, of course, but it's not completely trivial to build model states. It's doable, but it's not easy for FCI. The twist is also not completely trivial, but we can discuss about that to check into finite size. Yes. The topological degeneracy is the degeneracy of the ground state depend on the genus of the surface. Okay. Right. It basically probes in which geometry you're on. So something which is highly non-local, like how many holes you have, that's something that the ground state will detect, which is not trivial if you think about usual spin system. Usually you don't care about what is the underlying geometry, like what is the underlying genus on the surface you're working on. So that's a big difference between topologically ordered phases and more traditional phases of matter. You can have a degeneracy. Yeah, right. So the thing is, once again, you see that as an experimentalist. The only thing that you have is the results of your numerical simulations. And the first one is the energetics, because to understand what's going on, you diagonalize a Hamiltonian. So that's the first thing that you will come out of your computer. This question: if you see a almost threefold degenerate ground state, would you claim it's a fractional chain insulated? I say threefold just to be careful. Threefold is about the Laufman state 1/3. If you have other fractional conformal states, like the Laufman states, you can build it for any fraction 1/q. It's actually q-fold degenerate. So threefold for the Laufman 1/3, fivefold for the Laufman 1/5. If you look at more complex states, they have degeneracy that is well known, tabulated, and that's the first signal, but it's first signature. But once again, my point was to say that Chauncey wave could have the same type of degeneracy, like a commensurate one. Yeah, but usually when you do an FCI, unless you really want to make your life more painful, you do it on a torus, because periodic boundary conditions are easier when you do that in both directions. Technically, yeah, if I was super rich and I could do that like on a pretzel where you have 3 holes, that would be like amazing. But unfortunately, I'm not rich, so I use a torus. Yep. Yes, a moiré state for fermions is 6-fold degenerate, so even. And the parity is not related to the parity of the underlying microscopic degree of freedom. The moiré state bosonic is 3-fold degenerate. as another example. Always odd, yeah, because the laughing state, remember, the degeneracy is encoded in the zi minus zj to the power m. But m is also related to the statistics, because if you have fermions, you need, like I was mentioning, m to be odd if you have fermions, m to be even if you have bosons. Yep. Like, how would I do that? Fractional quantum Mole effect, we do that all the time. We go from the sphere to the torus easily, because you can write down, you can solve the Lambda level when you have a monopole, a spherical, it's called a spherical harmonic, something like that. I don't remember the exact name. So it's possible to exactly do the calculation of the sphere. If I would have to do, the FCI on the sphere, that would be quite painful, because put a continuum model, I'm not even sure, but let's say on the lattice, clearly putting a lattice on sphere is usually not something trivial. It's doable, but it's not trivial. The simple stuff that you can do for an FCI is that kind of setup, which is, if you have a finite size from a topology point of view, cylinder with open boundary is basically like, like a sphere. Same genus. Well, the thing is, you will recover, in principle, if you make your cylinder infinitely long, which is what you do when you do iGeometry, then you will recover the degeneracy, the threefold degeneracy. Talking about laughing one, it's going on at 1/3. You would recover the topological degeneracy of 1/3. But if you have any finite size system, I would expect that you have only one state. The issue is, now you have an open system, so you have the edge modes. So it's actually not completely trivial to, to see what's going on when you have open boundary conditions. That's why many, if you want to, the first indication, I mean, I didn't talk a lot about the edge modes, which is very interesting physics also, of course, there. But if you solely focus on the bulk properties, that's why you use geometries which have, no edges, so be it the sphere or the torus. Right, so that's the spectrum for the Kagome for different system sizes, different properties. Just as an example, that's basically what you will do tomorrow. So what kind of properties, for example, are there when you do a fractional quantum Mole effect that are not there when you do an FCI? One of them is the particle Hall symmetry. It's not, so the particle symmetry that you have for fractional quantum Mole effect tells you that if I look at a system at filling factor nu in just one Lambda level, it's actually equivalent to looking at the same problem at filling factor 1 minus mu. So if you observe a fraction, let's say 1/3, you should observe a fraction at 2/3. And it's really due to the property of the Lambda level. If you work for a generic churn band, this feature is absent. More precisely, you see it in the case of the Kagome, where I take 15 unit cells, so 5 by 3. If I take 5 particles, filling factor 1/3. If I take 10 particles, it's 2/3. So they should be rated by particle Hall symmetry. And as you can see, the two spectra are widely different here. And the reason why is the particle symmetry, when you apply it to an FCI, will give you the same two-body Hamiltonian plus an additional dispersion. And it's a dispersion that is proportional to the interaction strength. So it's not like you can get rid of it by increasing the strength of the interaction. This term is proportional to the interaction. And it's enough to destroy, in some cases, your FCI at the filling factor, let's say, 2/3. So that's one example. You can try to extract the gap. So that's what you would get if you do that for the Kagome model that you will do tomorrow for different system sizes. As you see, things might vary quite a bit, but somehow it's not surprising when you think about what I've described about the Coulomb interaction in the Landau level. You still have finite size effects. They are just a bit more prominent here. One thing I did not mention as another signature for an FCI, remember that one of the hallmarks of all this business of topological interfaces is the nature of the excitations, like the quasi-holes or the quasi-electrons that we have on top of the Laughlin state. They have these charges plus or minus E3, and they have these fractional statistics. Numerically, you can actually look at these excitations. One way to do that when you actually work with the quantum Hall effect is by changing the number of flux quanta. It's a very simple exercise where you can write down the model states for the Laughlin plus one quasi-hole. It's just multiplying the Laughlin state by the product of the ZI. If you really look at the density, you create basically, you deplete your electron gas around the center of your droplet. And if you measure the charge that is, that you have removed here, it's exactly a E3. So that's one way you can write down the wave function. You can compute it, the defect of charge, and look, it's actually a fraction of the charge of the electron. If you insert more, of course, you generate more and more excitations. The thing is, of course, they will have also some dynamical properties. It means that you will have, if you do that, if you diagonalize your Hamiltonian with a bunch of quasi-holes on top, you will have several, many states here, and a gap. So here, these are just quasi-hole states. And the thing is, how many states, quasi-hole states you have, it's something that you can infer from the fractional quantum Hall physics. So that's another powerful signature that you do have fractional quantum Hall or FCI in your system, just by adding or removing unit cells, which is the analog of adding or removing flux quanta. So you can predict the counting. You can actually predict the momentum. There is one way to do that. You can work with the information from the fractional quantum Hall effect in its own Brownian zone that you can define. And for the Brownian zone of the fractional quantum Hall effect, which is usually pretty, which is larger because it's defined as the GCD of the number of particles in the flux quanta in the system, into the FCI Brownian zone, which is just defined by the number of unit cells in the X and the Y direction. These are some nasty formula that you have in the tutorial, and you can play with that and check that in your simulations you get the right count. All right, so the last 5 minutes. The elephant in the room, not me, I'm just talking, why do we see FCI everywhere? Once again, I only focus for, the whole talk is about 1/3, but you could do the same exercise with the other fractions. After all, if you think about, in FCI, we do have the dispersion. If you include it, you will not kill immediately your FCI. And it's so interesting because you can have the competition now between these, topologically ordered phases and, for example, Fermi liquid. If you decrease the interaction, if you go down to the non-interacting limit, this is what you will get, Fermi C. You can also have a charge density wave, another competitor. But if you really crank up, if your interaction is large enough that your band is almost flat, in which case you get an FCI. One option that people have investigated a lot over the last few years was I tried to see how close you are to the lowest Landau level physics. It has different names depending on the people. Ideal chain bands, vortexable bands, or generalized Landau level. All of them are equivalent. Maybe, at least in the simplest case, without entering too much into the details. So that's the picture, for example, for the generalized Landau levels. It's just mean that you're dealing with a Landau level with a non-uniform metric and a non-uniform magnetic field. And you can show that, well, this is like equivalent to the two other approaches. I think maybe Professor Yu will talk about quantum geometry and stuff like that. So talking about the trace condition, which is the definition for the ideal Chern band. For flexible band, it's a very neat idea of, you know, if you look at the Landau levels, the wave function, the single particle wave function, it's the z to the m. So actually, it's very nice because it means that if I give you the orbital with m equal to 0, I know how to get the m equal 1 by multiplying by z. I can go on and multiply by z's, and I will recover all the orbitals like this. Of course, if you take you know, a band with the block wave function, there is no notion of multiplying by a z. So vortex stability is one way to try to have the analog of multiplying by z to taking from one block state to get all the others. It's a very nice framework because it allows you to do actually a bit more analytical calculations, but it's not a requirement. There are many counterexamples where you're far from these situations here where you see an FCI. And my point is it's actually very hard to infer if you will have an FCI or not, based, for example, on the Berry curvature or the quantum geometry of your band. Is it surprising? No. Remember when I was discussing, depending on what interaction you take, if you will get a Laughlin state or not. We don't have any analytical derivation of, oh, if this is the interaction, then you will have a Laughlin state. So it's not surprising that these simple one-body ingredients are not enough to capture or to tell you if you will get an FCI or not. Of course, if you're very close to a Landau level with the right interaction, yes, but it doesn't have to be. And that's maybe the reason why also we observe in experiments, because FCIs are robust. They are not fine-tuned points. And I think I'm out of time. So we will do the case of twisted demo T2 tomorrow. Thank you.
We had questions during the talk, but are there any other questions?
So your last comment there was it implying that a fractional Chern insulator doesn't have to be a Laughlin state?
No, my point was to say you have a nice framework that basically try to connect FCIs to lowest Landau level physics. Because the point was to say, well, I want to know without doing any numerical calculation if I will get an FCI. And without doing any calculation means that you're basically stuck to some extent to the one-body physics. So all these proposals here are based on looking at the one-body physics and try to decide if you're close enough to the Landau level and then you don't take a crazy interaction, then yes, you should get an FCI. But it's not about moving away from the Laughlin physics, which is a different question. Once again, let's to be clear, the Laughlin wave function or the Laughlin state is just a good approximation. It's not, I mean, if you do any numerical simulation for anything but the V1 interaction, you will not get the Laughlin state. You will get something slightly different. Actually, if you think about overlaps, there is it's guaranteed that the overlap between the Laughlin state and the ground state will go down to 0. Because if you have an exponentially growing Hilbert space, you take the overlap between two vectors, either they are 1 exactly, or at some point they will decay into 0. So the momentum sectors in which your state appear, depending on the geometry, some charge density wave will have different momenta from the FCI. If you pick the right geometry, that's one indicator. You can look at the density, the density correlation. If you have a charge density wave, they should be peaked around the typical momentum of the charge density wave, which is something that you will not get if you have an FCI.
Okay, let's thank Nicolas again.